Let us look at symmetric functions of roots. Now, starting with quadratic equation, let's take an example. X square plus 5x plus 6 equal to 0. This can be factored into x plus 3 times x plus 2 equal to 0. So that the roots are alpha equal to minus 3 and beta equal to minus 2. Here, we have also seen minus 3 plus minus 2 is equal to minus b by a, which is equal to minus 5 by 1, which is minus 5. And minus 3 times minus 2 is equal to c by a, which is 6 by 1, which is 6. This is pretty straightforward. But the interesting aspect is interchanging the roots alpha and beta does not change the value of these expressions. So instead of saying minus 3 plus minus 2, if we say minus 2 plus minus 3, we get the same result. Similarly, minus 2 times minus 3 is 6. So even if we interchange alpha and beta, the value of these expressions do not change. So in general, for a quadratic polynomial, alpha plus beta is equal to minus b by a, alpha times beta equal to c by a. So now, what we are going to do is define a function g of alpha comma beta equal to alpha plus beta. And another function by interchanging the roots alpha beta. So we have h of beta comma alpha is equal to beta plus alpha. So here we are interchanging the roots. As we have seen, g of alpha comma beta is equal to h of beta comma alpha. Similarly, p of alpha comma beta is equal to alpha beta, and q of beta comma alpha is equal to beta alpha. So again, p of alpha comma beta is equal to q of beta comma alpha. So basically the same thing, the numerical example that I took, I'm putting it using symbols. That's the only difference as of now. Now, any polynomial function of the roots which remains unchanged when any two or more roots are interchanged is called a symmetric function. So in case of quadratic, of course, there are only two roots. Or more comes when we look at higher degree polynomial equations. Now, let us look at functions of roots which are not symmetric. So here, of course, straightforward, we looked at alpha plus beta and alpha times beta. Remember, these are not the only two functions which can be symmetric or that can be formed using these roots alpha beta. We can create any other functions as well. For example, we can say p of alpha comma beta is equal to alpha square plus beta. Interchanging the roots alpha and beta gives us what? It gives us q of beta comma alpha is equal to beta square plus alpha. Okay, which means what? These two are not going to be the same. Here we are taking the square of alpha, here we are taking the square of beta. So they are not going to be same. Less, of course, alpha and beta are 1. So 1 square is 1, 1 square is 1. Or minus 1. Minus 1 square, minus 1 square. Now let's look at another one. M of alpha comma beta is equal to alpha minus beta. In this case, what happens? When we interchange alpha and beta, we get n of beta comma alpha is equal to beta minus alpha. These two are not going to be the same. If alpha is, let's look at this example itself, minus 3 and minus 2. So minus 3 minus minus 2, which is minus 3 plus 2, that is minus 1. So here we get minus 1. Here what happens? Beta is minus 2 minus minus 3. So minus 2 plus 3 gives us 1. So here it is minus 1, here it is plus 1. So m of alpha comma beta is not equal to n of beta comma alpha. But what about functions of roots of a cubic polynomial? So now let's look at the same concept of symmetric functions of roots using a cubic polynomial roots. So now we have a cubic equation, ax cube plus bx square plus cx plus d equal to 0. Let alpha, beta, gamma be the three roots. Then we have seen already the, in a previous session where we looked at the relation between coefficients and the roots of a cubic equation. We have seen that alpha plus beta plus gamma is equal to minus b by a. Alpha beta plus beta gamma plus gamma alpha is equal to c by a. And alpha beta gamma is equal to minus d by a. Now let the left-hand side expressions be defined as functions. So these are again going to be symmetric functions. Exchanging those roots are not going to change the value. So we can define many other functions involving the roots. Some are symmetric functions while others are not. Now, instead of writing the sum of the roots and the sum of the products of the roots taken two at a time, we can use a powerful notation because it's going to be painful to write it again and again. Alpha plus gamma, alpha beta plus beta gamma plus gamma alpha, and so on. Especially if we get into much higher degrees as well. So the notation is alpha plus beta plus gamma is equal to summation of alpha or sigma alpha. Alpha beta plus beta gamma plus gamma alpha is equal to sigma alpha beta. The symbol sigma is called summation and its use is called sigma notation. So here you notice we are just showing alpha with this notation. What we are supposed to do is take alpha and then keep adding the other roots, alpha plus beta plus gamma. Same here, we have alpha beta. So we are supposed to take two of the roots and then add to the other two roots, or rather sum of the products of the roots taken two at a time. Now, in the sigma notation, context tells us the number of roots involved, because we should know now when to stop. If somebody just gives us sigma alpha, we start off alpha plus beta plus gamma. So when do we stop? So that is given to us by the context. The highest degree of any single root appearing in a term is called the order of the symmetric function. For example, in sigma alpha beta square gamma to the power of 4 is equal to, so this would be the expansion of this, alpha beta square gamma to the power of 4 plus beta gamma square alpha to the power of 4 plus gamma alpha square beta to the power of 4. Now here, take any one term and look at the highest power or highest degree of any single root. So here highest is 4. So the order of this is 4. The sum of the exponents of all roots occurring in any term of the function is called the weight of the function. So here, take any one term and just add up the powers. 4 plus 2, 6 plus 1, 7. So in sigma alpha beta square gamma to the power of 4, the weight is 7. That was symmetric functions of roots. In the next session, we will look at some examples that would make it much more concrete. That's it for now. Bye.